Where to start? Does anybody got anything they want to talk about from the homeworks? We'd assigned like 1 through 15 at this point. If there's any questions.
It was like the second or third category on the Delta map. I think what it was. Just like let me look. What find it on Delta map. But there was like one set that was weird. No, probably didn't do it. The master product trinomial factor. That's the one.
So, yeah, sure. All right. So the idea here is we want to start by finding the two things that multiply to give us the leading coefficient times the constant term, and then also add to give us the middle term, the linear term. So what are the two things that multiply to give us -4 and add to give us +3? 4 and -1, right? So this is the master product. That's what's going to go in there. But keep in mind that 4 and -1 do not take us straight to the answer. All it's going to do is describe to us how to break apart the 3x. Hi, Miss Anderson. What's up?
Can I talk to Jeff for a few minutes?
Sure. So we'll break that 3x up into 4x plus -1x. And it doesn't matter if the -1x plus 4x, the order there doesn't matter. We'll make a group. From the first group, there's a greatest common factor of x. From the second group, there's a greatest common factor of -1. So now if I think about these as two separate terms, they have an x plus 1 in common. That leaves me with the 4x minus 1 as my leftover. And now I'm in a spot where I can solve. So that's the idea. So for master product, I would have typed in the -4. And then it accepted that, and my solutions were -1, and then an additional solution I would say is 1/4, is what we had found. And boom. Yep. But that's the idea. All right. Any others on questions? Okay, let the learning begin then. We're going to be looking at 13.3 today. And to start 13.3, we're going to start by getting in our time machine. And we're going to be going back in time to, I don't know, 6th grade or so. Maybe you had a problem like this, like 3,458 divided by 39. To do this kind of a problem, what did we do? What was it called? Long division, yeah. So like the 39 goes on the outside, the 3,558 goes underneath. It's just a little bit of vocab. This number is the dividend. This number is the divisor. So we start, okay, how many times does 39 go into 3? Well, none. How many times does 39 go into 34? Well, none. How many times does 39 go into 345? Well, probably 9. Let's look. 270 plus 54 is like 325 or 324. That looks right. And then we'd like subtract down. And we ask ourselves, okay, how many times does 39 go into 218? What's that gotta be? 6 probably. 180 plus 54 is, nope, that's too many. 5 then. 150 plus 45 is 195, and we subtract down. So that's going to be 23. So that's like our remainder. Everybody kind of remember doing this? So we'd say our answer then could be 95 plus 23 over 39. Again, we call the 95, that's the quotient. The 23 is the remainder. And the 39 is still your divisor. So just as like some vocab review while we're doing this. Does everybody kind of remember long division from way back in the day? You don't have to be like long division masters here, but it's going to get a little bit more complicated here because today we're not going to be talking about the division of numbers, but rather we're going to be talking about the division of polynomials. So we're going to talk about 2 types of polynomial division today. So we'll start with the more versatile type, this long division. So for example, if I have the polynomial here, 2x cubed minus 4x squared plus 5x plus 1 divided by x squared minus 3. Remember that a fraction is the same thing as division, right? So we'll set this up the same kind of way. So we'll have the divisor on the outside, and then the dividend kind of goes underneath. But if I look at this, I notice something kind of off about my divisor. What do you notice that's kind of off about that divisor?
And it looks almost like you get a little, it's not a problem, it's like an equation, right? Because it's not like some.
Well, it's just we're doing a division problem, right?
Yeah, you got like a polynomial.
Yeah. Yep. We're doing polynomial division. Nicole. It's not a difference of 2 squares because 3 isn't a square number. I mean, you could write as the square root of 3, but like that's not far off. But that's not where I'm getting at either. Where's the x terms? Well, we go from x squared to minus 3. What should be in between?
X.
There should be an x there, right? So before I get started on this, I want to make sure that all of those are represented. Now, there's no x's here, but I still want a place for that. So I'm just going to add a 0x term in there. And that'll make my life easier as I go through doing this problem, because it'll keep everything all the like terms lining up. Now, if I don't include that, as long as I'm paying attention, it's not a disaster, it's still recoverable. It's going to be inconvenient. But it's really easy to do something silly like add 6x squared plus 5x because they're lined up, even though they weren't like terms. If you include those guys like that, everything will line up and you won't be tempted to make such a silly mistake as to add unlike terms. So the way that we're going to start this, oops, and I wrote down a squared here. That was a cubed. Okay. The way we want to start this is I want to ask myself, what times x squared gives me 2x cubed? So what times x squared gives me 2x cubed? 2x. Everybody feel good about that? And all I care about initially are those leading terms. So I don't care about anything else. Everything else is just kind of along for the ride. Once I've figured out that first question, I'm then going to multiply that 2x to everything in the divisor. And then write the result underneath, and then we'll subtract down. Now, one of the most common mistakes I see students make on these kinds of problems is goofing up their negative signs when they're doing the subtraction. So what I would encourage you to do is to distribute that negative through. So I'm going to distribute that negative through, so the positive 2x cubed becomes negative, the positive 0x squared becomes negative, and the negative 6x becomes positive, and I'm just going to erase out the parentheses there. Yes, Josh? Sure. So far, so good. And then we're just going to add down. So positive 2x cubed plus negative 2x cubed, well, that just gives me 0. And then I have negative 4x squared minus 0x squared. Well, that's still just negative 4x squared. And then 5x plus 6x is 11x. And then I'll bring down that plus 1. And I'll go back to the top and ask myself, okay, what times x squared gives me negative 4x squared? Negative 4. And then just like we did before, I'm going to multiply that negative 4 by everything in the divisor and write it underneath. And then subtract down. Once I've done that, I'm going to distribute through my negative. And then we're just going to add down. Negative 4x squared plus 4x squared gives me 0. 11x minus 0x is still 11x. And 1 minus 12 is negative 11. So that's like my remainder. So we'd write as our final answer to this problem, we'd say that this is equal to 2x minus 4, that's the quotient, plus my remainder over my divisor. Is everybody okay with what we just did here? Again, you see now why I started with regular long division, because it's essentially the same process. Just wanted to get us kind of warmed up and seeing the similarity between something we already know how to do and this. Ideally, you remember this from last year, from Algebra 2. Most of us did this and did a pretty good amount of it. The catch here is that this is kind of a long process, right? That takes up a little bit of space. There's lots of places to make a little goof, to make a little mistake where you drop a negative or you combine two like terms that aren't actually like terms, or you just, like you copy something down wrong. There's lots of opportunities to make a little mistake. So ideally, we want to build this into maybe a more efficient process. The first step along the way is this observation called the remainder theorem. And what this says is...
Just whenever. This is early.
Okay.
Sorry about it.
No problem. What this says is that if I have some polynomial f of x, and I divide it by some other polynomial x minus k, so that's a polynomial with a degree 1 and a leading coefficient 1. Those type of polynomials have a special name. They're called monic polynomials. Then the remainder of that division problem is going to be the same thing as f of k. So if I just plug in k into my function, I'll get the same thing as the remainder as if I did long division. So let's just kind of illustrate that for you. So let's say that my f of x is 2x squared minus 5x plus 4. And I want to find f of 2. Well, I can always just, f of 2 just means we plug in, right? So that just gives me 2. Or if I take 2x squared minus 5x plus 4, and I divide it by x minus 2, I should get the same results, right? So we'll ask ourselves, what times x gives us 2x squared? That's just 2x. So I have 2x squared minus 4x. And then I subtract down. Gives me 9x plus 4. So 9 times x gives me 9x. Oh my gosh, it doesn't give me 9x, you dope, Mr. Kulik. Gives me negative 1x. Great googly moogly. Right, negative 5 plus 4. Ah! Look at how easy it is. Anyway, so I should have a negative 1 up there, and I go through, I have negative 1 plus 2. I subtract down, and I end up with 2. So we're getting the same result either way. Which one of those seems like the better way of doing it? If all I'm looking for is the remainder, boy, I'd rather just like do the substitution than the long division, right? That feels way simpler. And you're dead on there. Now, of all the division problems we have, there's one remainder in particular that's really important. What remainder is going to be the one that we're going to be the most interested in?
First one?
No, I mean like what number? Like remainder 5, remainder 12, remainder, not remainder 1.
2.
Not 2. Not 5. 0. Very good. Why are we be concerned about remainder 0? Because what that's going to mean is that number was a factor. So for example, if I have 6 and I divide it by 3, my answer is 2, remainder 0, right? And that's important because what it tells me then is if I take my quotient and my divisor and I multiply those back together, I'm going to get the dividend. 2 times 3 gives me 6. So what I'm able to do if I have a remainder 0 is I'm able to at least do a partial factorization. That's the key. So with that, we're going to form what's called the factor theorem. So the factor theorem says if I have some polynomial f of x, and it has a factor x minus k, if and only if that substitution gives us 0, i.e. it's a 0 remainder, which is just exactly the idea that we had before. All right, so example says show that x plus 3 is a factor of 6x cubed plus 25x squared plus 16x minus 15. Well, I know that if the remainder is 0, we have a factor, so I could do long division to do this. So what times x gives me 6x cubed? Well, that's 6x squared. And then if I subtract down, and then what times x gives me 7x squared? Well, that's 7x. And then I subtract down. And then what times x gives me negative 5x? Well, that's negative 5. Subtract down, I get remainder 0. Or, if this is x plus 3, k would be negative 3, right? So I could just look at f of negative 3. So let's see, negative 162 plus 225 minus 48 minus 15. That does give me 0. Notice that they're both telling me the same thing, right? That x plus 3 is a factor. We can say that 6x cubed plus 25x squared plus 16x minus 15 factors to x plus 3 times something else, right? Now, here's the catch. If I'm doing the long division, that other thing is the quotient. If I did the substitution, I don't know what that other factor is going to be. There's no way for me to get it from the substitution. What we would like here is a method that's as easy as the substitution, but I still get that quotient out of it so I can do a factorization when I'm done. So that's the holdup, right? We've seen over and over again that like the substitution racket was like easier than the long division, but here we're finally seeing why we still care about the long division is it gives us more information. It allows us to factor something when we're done with the division, where the substitution does not. Now, with that in mind, we're going to introduce a second type of polynomial division. That second type is called synthetic division. Now, synthetic division is going to be easier than long division. It's going to feel like the substitution, which is great. That's so easy in comparison. It's still going to give us a quotient back, which is great. That's all the extra information I'm getting from the long division. But there's a catch. The catch with synthetic division is it doesn't work for all polynomials. It only works if the divisor is monic. Something like x minus k. Well, that's okay. That's pretty good. That's going to cover most of the stuff that we really want to deal with. So I'm pretty happy about that. So just as a reminder of how that synthetic division works, let's say again, we'll take this same polynomial we've been working with in our examples here, and this same division problem. So what I do is I start by taking the divisor, I set it equal to 0, and then solve. So I get -3, right? So the setup for this is I'm going to have my new division, my synthetic division bar. The solution to the divisor set equal to 0 is going to be right there. Hi, Carrie, what's up?
You can borrow a few of your students if that's okay.
Okay.
You need Nicole Betancourt, Tia Karula, and Aaron Delaney.
Okay.
Thank you. Yeah, sorry.
It's okay. So that's my initial. And then
Three are in apart and set apart. Okay. Which one you use Tia? Okay. You guys will use. Okay. Now, are you sure that you guys have
and the coefficients from the dividend go in there. Does everybody feel okay with the setup so far? Now, what do we have to be careful about here? We have to be careful about skipped terms. So if I went from x cubed to x's and I didn't have any x squareds, I have to remember to include a 0. When we did the long division, if we're observant, we could still recover from that as long as we recognize that, oh, I make sure I got to add like terms. So, but here, and we're doing synthetic division, there is no recovery. If you miss putting in the 0, you're just not going to get the right answer, and you probably won't even notice that you didn't get the right answer. Everybody okay so far? So that's how we set it up. And the last one is we just execute the procedure. So the first step is we just bring that first number down. And then what I do is I take the outside number, multiply it by the one on the bottom. I write it in that next spot. And then we add down. And then I just keep repeating that process until I am out of spots to put things. Everybody's cool with the procedure. Again, I expect that we saw this last year in Algebra 2, so I don't have to do like a trillion practice examples of how to do the synthetic division. Something you probably did a fair bit of. But certainly I want to review. And then the last thing I want to do then is interpret the last row. So this row here. So the numbers at the bottom of the last row all have a meaning. We're going to read them from right to left, which is opposite direction of how we usually read things. So the first number, the 0, is our remainder. The next number is our constant term. The next number is the x coefficient. The next is the x squared coefficient, and so on, where everything after that first number on the right is describing our quotient. So from this synthetic division problem that we just did, we did 6x cubed plus 25x squared plus 16x minus 15 divided by x plus 3. And we found that that is equal to 6x squared plus 7x minus 5. And if I multiply both sides by x plus 3, what I have now is a partial factorization for my polynomial. Right? So the takeaway here is great. We've updated this long division procedure into something that's easier to execute, takes up less space, less time. That's much, much faster in practice than long division. It's much easier to execute. There's less opportunity to do something silly because it's just whole number operations for the most part. Fantastic. Gives me all the same information as the long division because I get the quotient and the remainder out of it. Fantastic. Now I can only use it some of the time. Okay, great. But Mr. Kulik, the catch here seems to be that how do I, like this worked great because we had a divisor to start with. We had a factor. How do I find a factor just as a starting point to start this synthetic division thing? Like you've told me the starting point before, right? Like x plus 3 is a factor, if you don't tell me that, how do I do this? That's the natural next question if I'm going to try to factor these things using division. That's the next question, because what we're really trying to do here, let me go back to 2 days ago. So you remember when we talked about factoring before, we drew this big factoring tree, right? This decision tree that helped us factor. What we've just created, right, is a way to fill in some of these blanks, right? If our polynomial wasn't in had 3 terms and not in the quadratic form, there was nothing we could do. If our polynomial had 4 terms and we couldn't factor by grouping, there was nothing we can do. If our polynomial had 5 or more terms, there was nothing we can do. What we're about to begin here to the end of chapter 13 is going to be filling in that procedure of what can I still do if this factoring tree fails, right? Now I can do my synthetic division techniques. We're going to fill in, build out how that technique is going to work, how to make choices in terms of finding that initial factor to get started. That's going to be the plan here for the rest of today and then the next lesson. Okay, so that's the context. So we need to figure out a way to find a starting point. So to do that, I'll explain what I did as a student, and then some of the advantages that you guys will have given the technology available to you as a student. So what I would have done to do this type of problem is I would have applied what's called the rational zeros theorem. And it says that every possible rational solution to our polynomial, or rational zero for our polynomial, is going to be of the form P over Q, where that P is every possible factor of the constant term, and the Q is every possible factor of the leading coefficient. So what that's going to do is it's going to give me a list of possible starting points. And when I was a student, you basically just had to guess. There was some other stuff that we can use that I'll show you that would allow us to get more than one thing checked at a time, but we'll be able to do even better than that given the technology available to us as an average student. So it says, make a list of every possible rational zero for the polynomial f of x equals yada, yada, yada. So I'm going to start with my constant term, which is -4, and then my leading coefficient, which is 3. What are all the factors of -4? What are all the numbers that divide -4? 2. What else? 4 and 1. You're missing 3 of them, though. Excellent. Yeah, so there's, if a positive divides it, obviously the negative does also, right? And then what are my factors for 3? Plus or minus 3 and plus or minus 1, right? So what that's telling us then is my possible rational zeros are going to be one of those factors divided by one of those factors. So I could have 1 over 1 or -1 over 1 or 2 over 1 or -2 over 1 or 4 over 1 or -4 over 1 or 1 over 3 or -1 over 3 or 2 over 3 or -2 over 3 or 4 over 3 or -4 over 3. Is everybody okay with how I've enumerated that list? Now that stinks to write out. What we're going to do instead is we're just going to agree that we can just write it this way, because woof, if there's like, you could end up with 20 or 30 or 40 of these possibilities really quickly, and yuckarooskies, I don't want to have to write that all out. Let's just write it this way. Everybody cool with that plan? We're good that those are equivalent expressions. We're going to agree that they are, so that we can use that shortcut of a notation. Okay, so now when I was a student, I would just randomly, blindly pick one of these values and try to do the synthetic division and see if I get a zero remainder with it. Now, there was another theorem that I would use in conjunction with this, that depending on what my division result looked like, I might be able to eliminate more than one of these. So let me put that in here for us and talk about how I would have used that. So it says if f of x is a polynomial with a positive leading coefficient, and we divide by k using synthetic division, if that k is a non-negative number, and then every number in the bottom line is non-negative, then k is an upper bound for all the real zeros of f. So for example, maybe I would have tried dividing by negative or by +1. If I did that and I got the bottom line of my synthetic division being all numbers that were non-negative, would tell me that 1 is an upper bound, so 2 and 4 and 4/3 couldn't be my answers either. So I wouldn't just be able to cross one number off my list of possibilities. I got to cross 4 numbers off my list of possibilities. Which is like, it ain't nothing. Is it the greatest thing in the world? It felt like it at the time, because boy, if I could cut this job of checking, anything I could do to make that a little shorter was helpful. The other option is if k is a negative value or a non-positive, and every number in the bottom alternates as from non-negative to non-positive, then k is a lower bound. So say, for example, I picked -1 and I got that alternating bottom row. It would tell me that -1 is smaller than all the possible answers. So anything smaller than -1, I could throw out. So again, I could discard -2, -4, and -4/3, which again, is that the greatest thing that's ever happened to me? No, but boy, that's helpful if I'm just tootling around in here blindly. that I am able to get like 4 for the price of 1. I was pretty excited about that as a student, because as you might have guessed, this was kind of tedious. Now, we're going to do better than that. In a moment, we're going to talk about how we can use our calculator to get a much better idea of our starting point. But we can still use that theorem that we just discussed to deal with a problem like this. So this problem says to show that every real zero of the polynomial f of x lies on the interval from -5 to 4. So one way you could do this is by finding all the real zeros for this polynomial and having to do all that synthetic division process and like find and solve, and could be a rather difficult procedure. Or I can just apply the theorem above and do 2 synthetic divisions, one with the lower bound and what I notice is that these are alternating. And I'm done. I don't actually have to solve anything. And likewise, if I do the positive value, oops, that's not, it's 12. And because these are all positives, I can say that x equals 4 is a upper bound for the zeros of f of x. And that's going to be simpler than actually finding all the solutions and showing that they're in between there, because all I need to do is 2 synthetic divisions. And just look at that bottom row. Right, so like, does everybody feel okay? All right, let's do an example now and show you how we can apply our calculator to this to help us do that initial choosing in a very efficient manner. And that'll close, this will be the last example for today. Next time we'll close out this section by looking at the last little bits of optimization we can do to our procedure. All right. So we want to find all the real zeros for this polynomial f of x. I'm going to start by making my PQ list. So my constant term is -30. Factors for -30 are a whole mess of them. And then my leading coefficient is 6. My factors of 6, again, that's kind of a lot for such a small number. So my possible rational zeros are going to be some combination of something from that, right? So that's actually a pretty daunting prospect, is what I have. 1, 2, 3, 4, 5, 6, 7, 8, 32. So I have 64 possibilities here. Woof. Here's a way that I can get around having to do just a pure guess and check, is I'm going to go ahead and graph my f of x into my calculator. So I'm going to press the y equals button and then just type in the f of x from my problem directly into my calculator. And now we've been doing scatter plots and stuff in the previous chapter. I don't know where my window is at, so I'm going to just do a quick zoom standard. That'll set my window back to like a reasonable -10 to 10 window. So if I take a look at this, I know that every x-intercept is going to be the same as a 0 for my polynomial. If I look, I see 1, 2, 3 x-intercepts, or 3 zeros. If I go back to section 1, I know that I would have at most the number of our degree, which is 3. So if I have at most 3 and I can see all 3 of them, I know that, okay, that's all the possibilities. And if I look at where those are crossing, I see this one is at -1, 2, 3, 4, 5, -6. I see another one between -1 and 0. Yes? Did you do zoom standard to reset your window? Okay. Yes. Sure. And then I have my third 0 somewhere between, it looks like 2 and 3, right? Now, in addition to looking at the location of these x-intercepts, I'm also going to look at one other thing. So remember from that very first lesson, we looked at, did we not? Oh, there it goes. There it is. We looked at this bend, bounce, and straight piece. That'll tell us what the multiplicity for those zeros would be. So I'm going to take a look at my graph here and check. Each one of these all look like they're just kind of passing straight through. You guys agree with that? So they all look like they're going to be used just the one time in my polynomial division, which is great. So I'm just going to note those all as straights. Now, if I looked at my graph, like this one at -6, I'm pretty sure that's at -6. But between 0 or -1 and 0, I mean, I could have like -1/2 or -1/3 or -1/6 or -2/3 or -5/6. There's like kind of a lot of choices in there still. And between 2 and 3, I could have like 5/2 or 15/6, or, there's still kind of there's still some choices in there. you know, like, I'm not like super stoked to go like blindly stumbling around in there. So which one of these should I pick as my starting? The one that I feel the best about, right? If I feel like this one looks like a whole number value, I'm pretty certain from looking at the tick marks that that is is an actual x-intercept. And even better, there's no fraction for me to have to deal with. I prefer not to deal with a fraction when I do my synthetic division if I don't have to. So let's go ahead and execute our synthetic division now. So I get that remainder 0. That makes me happy. That means that this works. So what I can say is that this polynomial x cubed plus 23x squared minus 83x minus 30 is going to equal x plus 6, because this gave me a remainder 0. I know it's a factor, times 6x squared minus 13x minus 5. Remember, that's the numbers here. That's my quotient, my constant, my x coefficient, my x squared coefficient. Everybody feels so far so good? If I look at this polynomial now, I notice, wait a second, that's quadratic, right? Let's just try to go back to our factoring tree and use these methods where I can get away from having to guess at a possible 0 to do a synthetic division. I hate guessing. I'd much rather just like, you know, be certain about it. So I'm going to look for two numbers that multiply to give me 6 times negative 5. So that's negative 30. And then add to give me negative 13. Does anybody see the two numbers that are going to multiply to give me negative 30 and then add to give me negative 13? What was that? 10 and 3 multiply to give you positive 30 and add to give you positive 13. If you did them both negative, they'd multiply to give you positive 30 and add to give you negative 13. So it's not quite right. What's that? So negative 15 and positive 2 is what you're looking for. That will work. My suggestion is always to do the multiplication piece first. So again, those two numbers, the negative 15 and 2, don't give you your factored form. What they do is they tell you how to split the middle term so that you can do a factor by grouping. From the first group, we can take out a factor of 3x. From the second group, well, there's nothing, but I can always take a 1 out, right? And if I look now at each term, they both have a 2x minus 5 in common. So when I factor that out, I'm left with 3x plus 1. So if I go back here to the beginning, I can now write a complete factorization for my polynomial, right, at x plus 6. And now I can say 2x minus 5 times 3x plus 1. So that's my complete factorization. And then to find the zeros, if I just set this thing equal to 0, I get -6, 5 over 2, and -1/3. And if we go back and we look at the possibilities there, you'll see that both 5 over 2 and -1 over 3 were on my list of possibilities. So this is where we're stopping today. We did a whole heap of stuff today, and we built out a procedure to deal with this. At this point, you guys should be able to do numbers 16 to 35. So you guys can start on those. How did this feel today? I tried to tell it like a story. Was that effective narrative as to like what we're doing and why we're doing things and where we're going with this? When we're building a procedure, I tried really hard to make it like a story that has like a plot to it at least. It's maybe a little easier to understand and like maybe just a little more interesting if it feels like there's some context to what we're doing. I'm going to stop here though. Next time we'll finish up chapter 13. What else might happen next time that we haven't done yet in chapter 13? Yeah, that might be a good idea to be kind of up to speed on that. Okay, so that probably is coming. Any other questions for me before we sign off and let you guys kind of tootle around and get starting on your homework? Okay. Very good.